So what I've mentioned before is that really the ultimate goal of most statistics, at least other than for like gambling and odds and things like that where we might use probability, most of the time where we use statistics in real life is in research and in trying to help us make decisions that we hopefully feel confident about. So a business, the medical field, all of those things. So our ultimate goal is 2 items: 1, confidence intervals, and 2, hypothesis testing. So today is the start of confidence intervals, and today we are only talking about confidence intervals for the population proportion. So we will also talk about confidence intervals for mean, but today we're just talking about proportion. So one definition that you need to know is point estimate, because it will ask you what is the best point estimate of, and then it'll give you something that we're trying to estimate. So a point estimate is the value of a statistic that estimates the value of a parameter. So remember, statistic is for the sample, parameter is for the population. So yesterday we talked about p hat. Today we're estimating p, which is the population proportion. P hat is the point estimate for p. And then I put, again, just like yesterday, how we find p hat. We take x, which is the number of individuals in a sample that contain our desired characteristic, and we divide it by the sample size. When you are finding p hat in this section, we are going to round its value to 3 decimal places. A confidence interval, and typically I'll write out just CI instead of the words confidence interval, for an unknown parameter consists of an interval of numbers that are based on a point estimate. So our unknown parameter, meaning we don't know the population proportion, but we're trying to use our sample proportion to help us estimate it. And they, of course, are not going to be exactly the same. You can't expect the entirety of a population of perhaps millions of people to have exactly the same proportion as your sample that might only have 100 people. So that's where level of confidence comes in. It represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. So we talked about very early on in the course replication and how it's important in research to not just do something once with one sample, but to repeat it, because that's how we end up with confidence in our answers. So the level of confidence is going to be 1 minus alpha times 100%, where alpha is the area in the tails. So the tails are the far ends. And so if you are to be 90% confident, then that means that the area in each tail, because there's one on each side, is 0.05. Because basically the level of confidence is the area in the middle. So if 0.9 is in the middle, that means there's 0.1 left to divide evenly between 2 tails. That's how we get 0.05. In order to be 95% confident, each tail's area would then decrease to 0.025, 99%, 0.005. So obviously that alpha gets a little smaller as we become more and more confident. Z sub alpha over 2 is the critical value. And you're going to be asked for these. You're going to need these. So generally, I don't know why, because there's z-scores. So generally, we really round these to 2 decimal places. So we typically use 1.65 here and 2.58 here. This one, 1.96. Those are always the critical values for those levels of confidence. So those aren't going to change as we go. So I took this graphic to kind of help explain. So our population proportion is what is in the middle. And we are basically trying to decide how confident we are in the results. So it's saying whatever our confidence level is, so 1 minus alpha times 100%, that percent of all sample proportions lie in the shaded region in the middle. Those sample proportions result in a CI that includes the population proportion, meaning that the actual p-value falls somewhere in there. These guys show what lies in the tail. So these sample proportions result in confidence intervals that do not include the population proportion. So meaning these samples are kind of our outliers, the ones that we wouldn't expect to have our actual population parameter. So critical values, those are when it asks for z sub alpha over 2, that's what it's asking for. It's asking for the critical value. It represents the number of standard deviations that a sample statistic can be from a parameter and still result in an interval that includes the parameter. So what we mean by interval, a confidence interval is kind of like casting a net and trying to make sure that wherever your net lands, that population proportion is somewhere in there. So that's what our critical value is. We're saying, okay, if I want to be 90% confident, then I could have a sample p hat that's 1.65 standard deviations away from the actual population parameter, but it still have p in the net. So we're trying to just make sure that we get p in the net. We don't have to be exactly this is p. We're just trying to find an interval that contains it. Margin of error is the maximum likely difference between our statistic and our parameter. And this is the formula for margin of error. You take the critical value, z sub alpha over 2, and you multiply that by the same formula that we used yesterday for calculating sigma sub p hat, except that this is p hat and q hat instead of p and q. There are 3 different ways to write a confidence interval. Make sure that you read the directions because it may tell you which format it wants the answer in. This format right here is called inequality format. And what it does is it puts the population proportion in the middle, and then it has a lower bound and an upper bound, which we get by taking our p hat minus the margin of error and our p hat plus the margin of error. This middle one, they actually just call it p hat plus or minus e notation. So if it asks you for this form, it will actually say write your confidence interval in the form p hat plus or minus e. And then this guy is interval notation, where you're using the same lower bound and upper bound that we had in inequality notation. We're just writing it as an interval. So it's going to be really important, and the same is true when we get to hypothesis testing in the last chapter. There are several things throughout this course where there's like a script, and you have to state things a certain way. It's going to ask you to find confidence intervals, but it's also going to ask you to interpret them. And the way you write it has to be very specific. It has to follow this script. So the way we interpret a confidence interval is we say we are blank percent. So whatever your level of confidence is, maybe it's 90%, maybe it's 98%, but whatever we're using in the problem, we are that percent confident that the, and then what you say is population proportion of, and then you describe whatever the situation is. The population proportion of, people who score above a 70% on their final, or whatever the real life situation is, whatever we're measuring, you describe that in the script. So we are blank percent confident that the population proportion of whatever the real life situation is, falls between, and then you list the lower bound and then you list the upper bound. And that's how we'll state it, and we'll obviously do that. There's one on the back where it asks us to interpret the interval, so we'll go through that script together as well. In section 8.2, we did a problem where it asked, how many more people would we need to sample? Similarly, these two are formulas for finding what our needed sample size is, based on our sample proportion and our critical value and our margin of error. So there's two different formulas, one for when we actually know the sample p-hat, and then one for when we don't. So when we don't, we use 0.25 here. The reason is that if we don't know p-hat, we assume p-hat to be 0.5 because 50-50 shot. And if p-hat is 0.5, then q-hat is also 0.5, and 0.5 times 0.5 is where that 0.25 comes from. Everything else about the formula is the same. I have also given you here the directions for StatCrunch. These are the directions for the confidence intervals. These are the directions for determining sample size, which I'll show you how to do those by hand as well. So example 1 asks us to determine the critical value that corresponds to a 98% level of confidence. So we have given up in this table the critical values that go with our 3 most common levels of confidence. But we can use any level of confidence, so we need to be able to find the critical value, the z sub alpha over 2 that goes with that. So the way that we do that is very familiar because it's what we've been doing now for a couple weeks. Since it's a z sub alpha, that means that my axis is z. And as I said before, the level of confidence represents the area that's in the middle. So if I have a 98% level of confidence, that means that the area in the middle is 0.98. Which that means that alpha is the complement of 0.98, so 0.02. And so the area on each tail is 0.01 because we have two tails always on these. And so what we're trying to find is this value right here. That z-score that represents the area to the right being 0.01. So we do this in StatCrunch using our normal calculator. So I'll type in this guy. Since it's a z-score, what are my mean and standard deviation? 0 and 1. So when I, hold on. So 2.33 is going to be my z sub alpha over 2. Again, we need to make sure that we can calculate any z sub alpha over 2 because they don't always use the most common ones. All right, example 2, determine the point estimate of the population proportion, the margin of error for each confidence interval, and the number of individuals in the sample with the specified characteristic X for the sample size provided. So what they've given us are the lower bound, the upper bound, and the sample size. So if I have the lower bound and the upper bound, what I should be looking at are these guys, because I know that my lower bound is p hat minus e. I know that my upper bound is p hat plus e. So my p hat has to be right in the middle of those, right? So if I add my lower bound plus my upper bound and divide it by 2, that has to equal my p hat, which is one of the things it asked me for. It asked me for the point estimate, which is p hat. So in this case, 0.201 plus 0.249 divided by 2. And again, as it said up at the top, we're going to round p hat to 3 decimal places. So p hat 0.225. So we found one of the things. We found the point estimate. Now it wants us to find the margin of error. So margin of error is E. So I can do this a bunch of different ways. I could subtract the upper bound and lower bound and then divide by 2. That would work. I could take the lower or upper bound and subtract p hat, and then that would give me E as well. There's lots of different ways to do that. I'm going to do margin of error equals upper bound, because again, if you look at our formula, our upper bound is p hat plus E. So if I take the upper bound and I subtract p hat, that's going to leave me with E. So upper bound minus p hat in this case, so 0.249 minus 0.225 gives me a margin of error of 0.024. The last thing it asked me for, the number of individuals in the sample with the specified characteristic X. So the only formula we have that relates both X and N based on something we know is the formula for p hat. So I know that p hat equals X over N. I know n, I know p hat, I'm looking for x. So plug in p hat, 0.225, plug in my value of n, which is 1200. And to solve for x, in this case, I would multiply both sides by 1200. Again, we're talking about individuals here, so we would want to bump up to whole numbers. If it comes out as a decimal, we wouldn't want a decimal. In this case, we just get 270. So whatever the characteristic is that we're measuring, in order to have that lower bound and upper bound for a sample size of 1,200, that would mean that 270 people had each of those characteristics. All right, does that make sense how I manipulated the formulas? Questions on example 1 or 2? All right, flip it then to the back. Example 3, we are constructing our first confidence interval for the population proportion. And in this case, they're not giving us the real life situation yet. We are just calculating. So we know that x equals 80. So 80 individuals have the characteristic out of the 200 that are in our sample. And we want to be 98% confident that the interval we come up with is going to catch the population proportion. That's what we're looking for. So we need to calculate p hat first. I'm going to do this one by hand. And then in example 4, we'll use the StatCrunch so you can see that. But it is important to know how to do it by hand as well with the formula. So p hat is what I'll calculate first. And even when we use StatCrunch in general, we have to usually calculate p hat. So 80 out of 200, which is 0.4. So p hat is 0.4. In order to have a confidence interval, I need p hat and I need the margin of error. So margin of error, we know that the formula starts with z sub alpha over 2. 98% confidence that z sub alpha is what we calculated in example 1. So I'm not going to do the work again. I already know what the value is from example 1. The z sub alpha over 2 is 2.33. The formula for margin of error, again, is right here. So I did z sub alpha over 2. Now I need to multiply that times the square root of p hat times q hat divided by n. So square root of p hat times q hat, what would q hat be? 0.6, good. And then divided by n, which is 200. So, I can type that all into my calculator. Most of the time, our confidence intervals for proportion, we use 3 decimal places and fraction. So 0.4 times 0.6 on the top, 200 on the bottom. And so 0.081 on this guy. And margin of error didn't tell us a specific to round 2 there. Okay, that's what I was looking for. So if you carry more decimal places than, for instance, someone else, I put the 0 and the 8 backward. said 0.081 and I wrote 0.80. So there we go for our margin of error. So it doesn't specify which format we have to use. Generally, if it doesn't specify, I use interval notation. So I'm looking for my lower bound to be p hat minus e, and then my upper bound p hat plus e. And so all I'm going to do is make those calculations. So 0.4 minus 0.081, and then over here 0.4 plus 0.081. So that is going to give me 0.319 on the lower bound. And on the upper bound, obviously, that gives me 0.481. So we're 98% confident that based on this information, that the actual population proportion would fall in this interval. All right, are we good on the by hand calculation? Okay, so now we're looking at a real life situation, and we're going to bring in our stat crunch here momentarily. So from a 3M privacy filters poll in which respondents were asked to identify their favorite seat when they fly, it says 492 of 806 chose the window seat. So part A asks us to obtain a point estimate of the population proportion of people who chose the window seat when flying. Now, that is certainly easy enough to do by hand, since that's just asking us for p hat. But in walking through, and I'll try to look from the side so you can see the whole thing, you go to stat, and then you go to proportion stats. Right now, we just have one sample, so we would choose that. The two ones that we are going to be looking at most are with data and with summary. With data is if they actually give you all the responses. So if you have to upload something from one of the files, that's when you would choose with data. Here we don't have that. We have with summary. So in here, yes, p hat is super easy to calculate ourselves, but just to illustrate that we can do that part in StatCrunch as well. The top, we type in the number of successes. So in this case, success would be chose the window seat. So I'm going to put 492 in for success. Number of observations is your N. So in this case, 806. And then below that, since I don't want to do this a second time, I'm going to go ahead and fill in the rest of what I'm going to do. So I'm not performing hypothesis tests yet. That's chapter 10. But I am trying to find a confidence interval. So I'll select confidence interval, and then I'm going to change my level of confidence. It is written as a decimal, not as a percent. So in this case, down in part C, it wants us to construct a 99% confidence interval. So I'm going to change that to 0.99 instead of 0.95. With summary, we choose, it always says leave the method as the standard walled. So you're not ever going to change this. And then we will click compute. So this is actually going to have our answers for both part A and part C, because it gives me my sample proportion right here. And then it gives you, this is the margin of error. And then this guy is the lower bound, and this guy is the upper bound. So that's giving us kind of all the information that we need to answer both of those questions. So for my sample proportion, again, super easy to do that by hand as well. If you wanted to do your 492 over 806, we're going to get the same thing. So 0.610 is indeed what StatCrunch told me if I round it to 3 decimal places like it says in our directions. I'm going to skip to C for a minute since that's what we had up on the StatCrunch. Use a 99% CI to estimate the proportion of the population who chooses the window seat when flying. So it is going to give us our lower limit and our upper limit. And so again, what I typed into StatCrunch was number of successes, 492. Number of observations was 806. And I put in 0.99. So this is telling me what you typed into StatCrunch, and then I can just write my answer. So 0.566 is what it says for the lower limit, rounded to 3 decimal places. For the upper limit, if I round it to 3 decimal places, it gives me 0.655. And this is all I would need to write. Now, Part B asks us to verify that the requirements for constructing a confidence interval about P are satisfied. So these are the same as the requirements we justified yesterday. So it doesn't matter what order you do them in, but I need to know that NPQ is greater than or equal to 10. So NPQ greater than or equal to 10. So N was 806 times P is 0.61, which means Q is 0.39. Obviously, that's going to be much bigger than 10. It's like 191.7. We need to know that it's simple random. As I said yesterday, the book problems aren't always good about making sure that it says that. But what they tell us is that if it's a real life situation where an actual company is conducting that we can assume that it is. So you can just write assume random. And then the other thing we have to check is that the sample size is less than 5% of the population. So N less than or equal to 0.5 capital N. So 806 less than or equal to 0.05 N. If I solve this for N, that would give me 16,120. Respondents are identifying their favorite seat when they fly. So that means that the proportion are people who fly on airplanes at some point. So I think we can agree that more than 16,000 people in the world fly on airplanes. So yes, these are all satisfied. Part D, interpret the intervals. So this is where we use the script. So we start out by saying we are, and then we insert the level of confidence, in this case, 99. So we are 99% confident that, and again, it's a script, you really have to follow it. It says the population proportion of, and then what was our success this time? What were the people doing? People choosing the window seat. So of people who choose the window seat when flying, falls between 0.566 and 0.655. Does that make sense how we plugged in the real life situation? Because that was kind of the part that was missing from the script. All right, last one. Example 5. Your plan to develop a new software system that you believe will surpass the success of Google and Facebook combined. In planning for the operating system that you will use, you need to estimate the percentage of computers that use Windows. How many computers must be surveyed in order to be 99% confident that your estimate is in error by no more than 1 percentage point? So again, this is us trying to figure out how many things need to be in my sample in order for me to feel that percent confident. So these are the sample size formulas. So down at the bottom, so we have 1 for when p hat is known, 1 for when p hat is not known. We need to know z sub alpha over 2. We need to know the margin of error. And again, if we know p hat, we use it. If we don't, we use 0.25 up here. I did give you directions for StatCrunch on these. I think it's just as easy to do by hand. So that's up to you. It says 99% confident. So that z sub alpha over 2, again, I showed you in example 1 how you can find any z sub alpha over 2, but this is one that's in our chart. So I just know that this is 2.58. So z sub alpha over 2 for that confidence level, I pulled from the chart, but you can use the normal calculator to find any of them. So my sample size is going to be z sub alpha over 2 squared. It says a recent survey suggests that 90% of computers use Windows, which means that they are estimating that p hat is 0.9. So that means p hat is known. If it's 0.9, then q hat is 0.1. Here's where it's a little tricky. The margin of error is right here. It's just worded weird. It says that your estimate is in error by no more than 1 percentage point. So what that is telling us is that our margin of error is 1%, which is 0.01. So that is what goes on the bottom, 0.01, and in the formula it is squared. And so then I would type all this in to my calculator. When I do that, it gives me 5,990.76. Just like we have on everything that is sample size, we have to bump this up because I can't survey a part of a computer. So I'll need 5,991 computers in my survey in order to be 99% confident in my estimate. In part B, assume nothing is known about the population proportion, so meaning I don't have a survey that gives me a p hat. So that means that I just change the p hat q hat to 0.25 instead. Everything else stays the same. And no, so the 0.25 comes from the formula directly. So z sub alpha over 2 squared times 0.25. But the reason it's 0.25 is because if we don't know, we're assuming that p hat is 0.5, which makes q hat 0.5 also. So then when I type this in, for some reason I did not write exactly what this gives me. 0.25 and 0.01 squared. Oh, that's why. I thought I didn't write it. It's because it actually came out to a whole number. So that's why I didn't round, because it is a whole number answer, 16,641. So notice this is a big difference. If you're conducting a survey, having a previous survey to work off of really helps us adjust our sample size. So this is a lot more than this guy as far as having to get the data. All right. Let me stop.